What's going on, everybody? You are about to get a taste today of an aspect of statistics that you see everywhere. You see it in a lot of different places. It's something called a confidence interval and allows for us to describe our predictions, our inferences, if you will, as not just a singular estimate, but rather a singular estimate with some margins of error, with some descriptions about how much uncertainty is associated with this particular estimate. And like I said here, you're really going to see this in a lot of different locations here. Here's an example here. This is actually from the 2008 election here, and it shows you the popularity, if you will, of the two primary candidates, Barack Obama and John McCain here. And you're actually seeing that at any given moment here, from March all the way to July, that there were some fluctuations in the popularity of one candidate versus another. But notice that even with a singular estimate here for Obama and for McCain, or here, that the estimate was not just given as a point. There's also a little bit of shading that's taking place here, some light red and some light blue here that describes the uncertainty that's associated with each one of these estimates here. It allows for us to be forthcoming about our findings here. You can actually see an indication here. This is called the margin of error, plus or minus 2%, plus or minus 2%. Remember that. That's going to come up in some of our own problems that we work on today. Here's another example. This is from our more present election here. This is associated with the Democratic primary here, listing some example candidates for the Democratic nomination here: Joe Biden, Michael Bloomberg, Elizabeth Warren, Bernie Sanders. And across here it shows likelihood of winning the Democratic primary. But notice even with these likelihood ratings here, there's a little bit of an interval that's associated with this. In fact, this is the correct terminology here, a 95% confidence interval. What it says here is that we're estimating his likelihood to win to be here, but within a 95% area of confidence, we can be 95% sure that his actual likelihood of winning, and I think actually by winning they mean beating his opponent, as being somewhere between here and here. So we can say with 95% confidence that his likelihood is somewhere between here and here. We also see this in climate change research here. We're showing most people don't realize that in climate change scenarios, there's actually more than one climate change scenario that's created by each one of the scientists. And these have to do with what different decisions world leaders might make in terms of how much we cut our carbon emissions. I mean, this is one in which we are really cutting our emissions very, very strongly here, and so the surface warming doesn't go up nearly as much. We have other scenarios in which people just say, screw it, let's just keep doing what we're doing, and as you can see, those outcomes are very, very different. But even with each one of those individual simulations, notice there is some degree of uncertainty associated with each one of the estimates here. So you can see that it's important for us to be very, very honest about what those uncertainties are. This is the same climate change research, but this shows specifically how much the sea ice at the North Pole is receding in size here. And once again, you can see different scenarios here associated with what we decide to do as a set of nations and as the world. But even within each one of those scenarios here, you can see a certain degree of uncertainty with each one of those. And notice, this is actually makes sense here, that degree of uncertainty kind of widens out over time because those uncertainties start to build on each other and they start to become wider and wider and wider as time goes on. So that makes sense. This is actually one that is more recent here. This is actually something that was put out. Actually, it was featured by Donald Trump in one of his recent briefings on the coronavirus. This is a computer model. I think it's put out by this guy here. I think he's at the University of Washington, in which he's attempting to see realistically what our curve is going to be. And how flattened is it actually going to be now that we're all sequestered in our houses here and we're trying to practice safe distancing and all that sort of stuff here. So as you can see, it looks like the number of deaths is going to peak somewhere around the middle of this month, the middle of April, and it's going to decline after that. It's going to peak, it looks like, at about 2,200 deaths a day. It's terrible, but that's it, could certainly be worse. But you can see here that there's some degree of uncertainty in those estimates here. It might be as high as 3,500, might be as low as 1,200. And so once again, we're seeing an instance here in which there's an area of confidence that's associated with some of these model outputs. And so that's the kind of thing we're going to be discussing here today. So it's very, very important that we get ourselves ready to focus on the now, to empty our thoughts, focus on our breathing, and to take control of the day in a way that allows you to sort of lose your mind and come to awareness. Take in the day. Take a moment to do that. Welcome back. Well, we're actually going to start where we were before here, but before we even do that, I'm going to give you a set of warm-up problems here. Let's take a look at our standard normal distribution here. This should be pretty familiar to you now. This is the normal distribution with a mean of 0 and a standard deviation of 1 here. And the question is, on the standard normal distribution, what value would these two z's have to be? I've got a z and a negative z here in order for 90% of the area under the curve to be between negative z and positive z. So think what that would have to be here and in order to make that happen here. So let's actually do this warm-up together. For this instance here, we want 90% of the area between these two values of z, and so if 90% of the area is here, then that means the remaining 10% has to be evenly distributed amongst these two tails here, so that means 10% here oh, I'm sorry, 5% here and 5% here. Which means that if I were to take a look at this one value of z here, that the amount of area to the left of this z value would be 90% plus 5%, or 0.95. Another way of saying 95% there. So the question is, and I'm going to use this notation here, z of 0.95 here, whatever, this is a way of saying what is the z value for which 95% of the area is to the left of that. So this is the notation I'd like for us to use for that. So what is the z value for which 95% of the data is to the left of that? And I'm going to quickly pull up here, oh, I forgot to do this, to pull up my normal distribution table here. Oh, good, it's right here. I'm going to bring this in here, and I'm going to zoom in. And so I'm looking for what's the value of z here that will make it so that 95% of the data is to the left of that z value. Well, here we've got 0.9495, and here's 0.9505 here. So let's actually just take a look. Let's round this to 1.64, or actually 1.65. Let's do that. So it looks like for 95% of the data, that z value has to be 1.65. So what is that? This is 1.65 here. So that means that this z value here has to be 1.65. This z value here would have to be negative 1.65, and there would be 90% of the area under the curve in between those two things. So then, how about 95% of the area under the curve? Let's move these z values out just a little bit more so that we hug not 90% of the data, but 95% of the data. How much bigger would these z values have to be in order to make that happen? Well, let me go ahead and erase some of this stuff here. All right, so instead of 90% of the data being in the center, now we have 95% of the data being in between z and negative z here. So what's left for these two tails? Well, that's just 5% split between the two of them. That means 2.5% here and 2.5% here. And so now, how much is to the left of z here? How much area is to the left of z? Well, it's 95 plus 2.5, or 97.5%, which as a decimal is 0.975. All right, so for this one, we ask the question, what is the z value for which 97.5% of the data is to the left of that z value here? And let's pull that up on our table. Wherever it is, here it is. So we're now looking not for 0.95, but 0.975. I have to find my mouse pointer here too. 0.975, and it looks like it's right here. Okay, so what z value is that? That's going to be 1.96. 1.96. So the answer is 1.96 here. So if we're wanting to define an area defined by a z and a negative z that has 95% of the data in between these two values here, then we want to have this z value be 1.96. 1.96 standard deviations out from the mean in the positive direction and in the negative direction. Okay, and that's bigger than 1.65. We have to push them out a little bit more, don't we, in order to get not 90% of the data, but 95% of the data. And now we're going to have to push them out even farther to get 99% of the data. And so I'm going to try scribbling here instead of erasing here. So now I want 99% of the data to be in between z and negative z, which means I only have 1% of the data to split between these two tails here. That means 0.5% has to go here, and 0.5% has to go here. And so now I'm asking our familiar question here, what percent of the data is to the left of z? That's 99 plus 0.5%, or 0.995 as a decimal, 99.5% of the data. So now I'm asking, what is the z value for which 99.5% of the data is to its left? Let's pull up our table again. So now I'm looking for 0.995 on this table here. 0.995. Well, it's between here and here, and it is 2.5 something. It is 2.5. Let's round it up to 2.58. 2.58. So in other words, if I want to create an interval, with z and a negative z, in which I'm hugging 99% of the data in between those two boundaries, then I want to put those z values at plus or minus 2.58 standard deviations away from the mean. Okay, you wonder how are we going to use that? Well, it's actually going to be very, very useful. In fact, this is probably one of the more important slides on this whole presentation here. We're going to be referring back to those numbers quite a bit here. So once again, let me just reinforce this new symbology here, where if I put a subscript here on z, that means that's the probability that a z value is less than this. So if I have something here that says 0.0005, that means to the left of it there's only this much of the area, so it's way over here. 0.025, it's also way over here, so it's got 2.5% of the data to its left. If this is z sub 0.05, that means it's over here but not nearly as much. It's got 5% of the data to its left. And if this is 0.95 here, that's way over on the other side here. It's got 95% of the data to its left, and so the probability that z is less than that is 0.95. In the same way, these two are out here at 0.975 and 0.995. Out here, they have 97.5 and 99.5% of the data to their left here. So I just wanted to get you comfortable with this notation here. And what we found was that we came up with these values here. These are going to be pretty significant. And let me get rid of my picture here so you can fully see them here. So there's a negative side to them, and there's a positive side to them. This, you can see here, this defines the tail to the left here. These define this tail to the right here. Okay, so let's, like I said, let's talk about some of the stuff we did last time here, where we are looking at a bunch of random numbers. I actually generated 1 million random numbers on this spreadsheet here. It's 10 columns rather, each column being 100,000 random numbers, each one between 0 and 100, and we're wanting to find out what is the average value of all of the numbers in this sample here. Well, I can tell you right now the right answer is 50.03. But if we were to sample all of them, we'd get this value here, wouldn't we? We'd be able to calculate this average, no problem. But what if we're not able to see all of the data here? What if we're not able to sample everything, but only part of it? Well, if we are sampling just 5 locations, there will be times when we'll think that the average is 20, and there will be times when we think that that average is 80, but there will be a lot more times in which we think that the average is between 40 and 60. So there's a distribution of possibilities here that we might get for thinking of what the average is. And it's got a mean that's around the right answer here, around 50 or so, but it's got a standard deviation that extends in both directions from that. Now you can see with a sample size of 10, we're still hitting the mean at the right point here, but we have instances in which we're concluding that the actual population mean is 30. Some places where we're concluding that it's 70. We don't have all the data here, and so there's a margin of error, isn't there? Now it's a smaller margin of error because now we're sampling 10 places instead of just 5 places, and we noticed that the standard deviation gets a little smaller here. Things get even smaller here with a sample size of 20. So that standard deviation gets smaller. Sample size of 50, everything is smaller still. With 100, things are even smaller. With 1,000, things are smaller still. And with 10,000, they're really, really small. You're getting, a pretty precise estimate here that the average is going to be 50 from 10,000 samples. And we would hope that we'd have a pretty solid, precise estimate from 10,000 samples. So you can see here that as the sample size gets bigger, we're pretty much hovering around where we need to be as far as the mean is concerned. But boy, our precision is getting greater and greater and greater. So as the sample size gets bigger, the mean stays the same, the standard deviation goes down. This also means that sample errors, standard errors go down, and so estimates of the mean are more certain for larger samples. So here's the standard error. We talked about it last time here, how that decreases as the sample size gets bigger. And here's our familiar equation here. We take the standard error and divide it by the square root of the sample size, where n is the sample size there. And we call this the standard error of the mean. And then we did, for example, this example problem here where Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours. Okay, so that's a mouthful there. So let's take this step by step. What we're getting here, first of all, is we're going to be calculating the mean number of hours they watch television. And let's first of all talk about what the standard error is going to be of that mean. Well, we're told that the standard deviation is 3 hours, all right? And we have a sample size of 20 children, so that the square root of 20 is going to be on the bottom here. 3 divided by the square root of 20 is 0.671. So that's our standard error for the mean. That gives us an indication of just how wide that little normal distribution is going to be as we estimate this, based on the fact that we are sampling 20 children. So where is this cutoff here of 26.3 hours on the standard normal distribution here? Well, the estimated value here is 26.3. Let's subtract that from the mean and then divide that by the standard error of the mean, and we have 1.94 standard deviations greater than the mean here. So we want to find the mean number of hours they watch television will be greater than 26.3 hours. What's the probability of that happening? So that's the probability that z will be larger than 1.94. That's the complement of the probability that it's going to be less than 1.94. So we take 1 minus 0.9738 and we get 0.0262. So about a 2.5% chance that the average number of hours that a sample of 20 children watch television will be greater than 26.3 hours. So that's stuff we've done before here. But, and notice, this involves us knowing what the right answer is. The average number of hours of television per week. We know what the population average is. It's 25 hours per week. But in the real world, that's not usually the case. We usually don't know what the actual value of mu is, what the actual value of the population mean is. But can we still use this value of the standard error of the mean to describe the margin of error on our estimate, on how much precision our estimate might have? So here's how this works here. Let's say that these numbers that we were working with before, the numbers between 0 and 100, let's say that these are approval ratings of the president. So they're numbers between 0 and 100. And each person gets to choose a number that's between 0 and 100. 0 means I don't like what's happening at all. 100 means very, very good. And what we can do is we can find out what all those numbers are for everybody in the country, and we average them together. That's what mu is. But we don't know what mu is. But what we can do is we can talk to 20 people. We can't talk to everybody. That would be too expensive. But we can talk to 20 people. And so when we talk to 20 people, we get an average value here of 48.9. All right, some people said more than 48.9, some people said less, but the average of these 20 people was 48.9. And let's take a look here. Let's say we know from some previous study or something that the standard deviation of this is 29.169 here. That if you took a look at individuals, throughout the country, and you had a normal distribution there, that it would have a standard deviation of 29.169. If you're looking at individuals here, so that's going to be a wide distribution here. We can use this and the sample size here to calculate what the standard error of the mean is. It's 29.169 divided by the square root of this, and we get 6.536. So what's the best estimate that we have of what this average rating is for the president? Well, it's this 48.9 here. It's only 20 people, but it's the best of what we've got here. And so this is our point estimate here. And we're going to put this right in the center of our confidence interval. All right, so our confidence interval is going to have this average here that we calculated right in the center. And then the question is, how long are each one of these bars going to be here? What's the margin of error? Well, as it turns out, it depends on a couple of things. And you'll see this in a moment here. So let's build our normal distribution here once again. The average here is 48.9. The standard error is 6.536. And so for a 95% confidence interval, that involves, from our warm-up, if you recall, a 95% confidence interval, that z and negative z value that we needed for a 95% confidence interval was 1.6 and negative 1.96 and negative 1.96. We needed to have 1.96 standard deviations out from the mean in order to get a 95% confidence interval. That's what you found in that warm-up there. And so that's exactly what we're going to do here. We start at 48.9, but we push out here this standard error times 1.96, whatever that is in this direction, and we do the same thing in the other direction here as well. So these two things here are called the margin of error. So for 95% of the area, this is what we do here. Let's find out what this is here. 1.96 times the standard error, that's 1.96 times 6.536, that's going to be 12.8. So our point estimate is 48.9, and we have our confidence interval here that is 12.8 more in this direction and 12.8 less in this direction here. So this is one way of putting it. We could say 48.9 plus or minus 12.8, or, and this 12.8, by the way, is what we call the margin of error right here. Or we can calculate what these things are here. 48.9 plus 12.8 is 61.7. 48.9 minus 12.8 is 36.1. So we can say with a 95% confidence here that the population average for the approval rating of the president is somewhere between 36.1 and 61.7. So let's first of all start off, that should say 90% confidence interval, that's featured here with that 5% on either side here. Here, if you recall, our value for z in both directions from the mean was 1.65. So it's that many standard deviations plus or added or subtracted from the mean here times the standard error of the mean. Whoops. So that's one way of putting it here. We can describe the standard error of the mean. We can put it this way. This is the exact same thing, except we've replaced the standard error of the mean with the formula for the standard error of the mean. That's another way of saying this. Here's a third way of saying this. We can say that the population mean is somewhere in between x minus this, x bar, so the average minus this, and x bar, the average plus this. Just another way of saying this. So these are three different ways of saying the same thing here. So whichever one feels most comfortable for you, you latch onto that one, but also be comfortable saying it these other two ways as well. So there's a 95% confidence interval here. For a 95% confidence interval, you can see this here. I downloaded this picture off the internet here, and you're not the only ones that discovered that in order to get 95% of the area under this normal distribution, you have to go out 1.96 standard deviations this way and 1.96 standard deviations this way. So this time it is the sample mean plus or minus 1.96 standard errors of the mean. All right, we can say it this way. We can be a little more explicit here by saying the standard error of the mean is just the standard deviation divided by the square root of the sample size here. We can say it this way as well. Or we can say that the interval here, the confidence interval for the population mean is somewhere in between the sample mean minus 1.96 of this and the sample mean plus 1.96 times this. Just three different ways of saying the same thing. And then for a 99% confidence interval, you figured this one out as well. You got 2.58 plus or minus 2.58 standard deviations in both directions here. So you can say that this way, you can say that this way, or you can say that this way. Okay, so let's describe this in terms of general terms here. Let's put all this together here. For a general 1 minus alpha % confidence interval, what in the world am I saying there? So let's say it's a 95% confidence interval here. That's, shouldn't have a decimal point there. That's the same thing as 0.95. All right, so 0.95 here is 1 minus alpha. In this case, alpha is the size of both of the tails here added together. Okay, so for a 90% confidence interval, alpha here is 0.1. For a 95% confidence interval, the size of the tails is 5%. And for a 99% confidence interval, the size of the tails is 1%. Okay, so for a general 1 minus alpha % confidence interval here, so you can see here, what's the connection between this and this? If I take this and subtract it from 1, I get 99%. If I take this and subtract it from 1, I get this. And if I take this and subtract it from 1, I get this. So you can see here that I can describe this in general terms here, a 1 minus alpha % confidence interval. Let's try a different one here. What if I had alpha equal to 0.02? All right, if alpha equals 0.02, then that's actually what kind of a confidence interval is that? Well, subtract this from 1 and I get 0.98. That's a 98% confidence interval. You see how this works? So we're just going to describe the confidence intervals in terms of this little alpha thing right here. And you'll see I use alpha here in some of our formulas here. So this is just a general way of describing stuff that I showed on previous slides here. So you'll get the idea here. For a general confidence interval, let's say that it's a 95% confidence interval, in which case alpha is 0.05. Then what we do is we take the sample mean plus or minus whatever this z value is here. If alpha equals 0.05, then that's going to be 0.05 divided by 2. Okay, so that's 0.025. Subtract that from 1. That's 0.975. Okay, well, this is what you did in the warm-up here. In order to get that 95% confidence interval, you had to find out what z sub 0.975 was. Okay, so this is just a formula that makes you go through that same process there of you divide these tails up between the two, this area between the two tails, and you add the center to one of the tails to get the area to the left of the z value. I mean, it's the stuff we did in the warm-up here. So this is just a way of calculating what z value you should use here for this. And just like before, you multiply this by the standard error of the mean, which can be represented like this, or like this, or you can describe it here as this and this. The population mean has to be somewhere in between these two things here. Okay, all of what we're doing here, by the way, makes some assumptions. These are important assumptions to understand here. First of all, the population standard deviation sigma is known. That's kind of unusual for the real world, but we'll get to what we do when we don't know this later on. So the sample is a random sample. It's got to be a random sample, not just I'll talk to 5 of my friends that I met on the way home from school. And lastly, either the population is normally distributed or the sample size n is greater than 30. If the sample size n is greater than 30, we saw this with the central limit theorem, where that sample size gets bigger and bigger, and this distribution of the sample means gets more and more like a normal distribution here. So either the population itself has to be normally distributed, or the sample size has to be big enough that the distribution of the means is going to be normally distributed. Here's an example of how we can use this. A researcher wishes to estimate the number of days it takes an automobile dealer to sell a Chevy Aveo. A random sample of 50 cars had a mean time on the dealer's lot of 54 days. Okay, so we're wanting to, let's actually just extract that here. A researcher wishes to estimate the number of days it takes an automobile dealer to sell a Chevy Aveo here. So this value of mu here, that's the population value, the population mean for time on dealer's lot. All right, it's the population mean. Do we know what this is? No, we do not. What we do know is a sample average from 50 cars. This was our sample mean for the time on the dealer's lot. And that value was 54 days. Okay, so that's our point estimate, isn't it? And that comes from a sample size of 50 cars. Okay, so we already know what x bar is, and we know what n is. Let's assume the population standard deviation to be 6 days. Okay, so we've got this now. This is sigma. So that's 6 days. Find the best point estimate of the population mean and the 95% confidence interval of the population mean. Okay, well, what's the best estimate that we have of mu? The answer is x bar. The best estimate that we have of this population mean, in other words, the time on the dealer's lot, is what we found for these 50 cars here. So our point estimate here is going to be 54 days, and that's going to be in the center of our confidence interval. I think I might have some stuff shown here. I think I'm going to erase this stuff here now. I don't want to get in the way of my animation here. Okay, so there we go. Let me switch back to a regular pointer. Okay, so we know that the x bar here is 54. We know actually that the standard error of the mean is going to be sigma divided by the square root of n. So 6.0 divided by the square root of 50, that's going to be 0.8485. So that's the standard error of the mean. That's how wide that little normal distribution is going to be for a sample size of 50. A 95% confidence interval means that alpha is 0.05, so you saw that from earlier, and so what we want to use is z of 0.975, which you found from the warm-up is this. You can just memorize, that for a 95% confidence interval it's 1.96. It's pretty common for people to just know that. And so that means that what we're going to find here is our confidence interval is centered at 54, but we're adding and subtracting this margin of error right in here. And this came from this, and this came from this. So the z value times the standard error of the mean. And these two things multiplied together is this, 1.6631. So this is our margin of error here, 1.6631. And so a way of saying that is that we can infer with 95% confidence that the actual number of days it takes an automobile dealer to sell a Chevy Aveo is somewhere in between this and this, 54 minus this and 54 plus this. In other words, 52.3 days and 7 days. 55.7 days there. Oh, let me get my face out of the way there so you can see, once again, this was the margin of error that we added and subtracted from 54 to get this interval here. That's our 95% confidence interval. So again, we can be 95% confident that the number of days it takes to sell an Aveo is between this and this. Here's another example. A large urgent care center with 4 doctors found that they can see an average of 18 patients per hour. Assume the standard deviation is 3.2. A random sample of 42 hours was selected. Find the 99% confidence interval of the mean. Okay, so this is another case in which you can assume here that we have our sample mean here of 18 patients per hour, and that's come from 42 hours being sampled, so that's our sample size here, and we know that the standard deviation is 3.2, so that's there, and we can calculate the standard error of the mean right here. A 99% confidence interval means that this alpha value is just 0.01, which means that the z value that we're dealing with, if you plug this into the formula, is going to be z sub 0.995. That from our warm-up was 2.58. And so here it's just, I know it's a jumbled mess here, but just understand what this is here. This is just that z value that you came up with here multiplied by the standard error of the mean. You multiply those two things together to get the margin of error that you're going to add and subtract from the point estimate here. And so we know that the number of patients that can be seen per hour, the actual number of patients that can be seen per hour, we can say with 99% confidence that it's somewhere between here and here. We can be 99% confident that the average number of patients that the center can care for is between 16.7 and 19.274. I mean, we presume that that's an average. You can't have, 0.7 people, and that's anyway. So that's an average of how many they can see. All right, so here's a problem to do on your own here. Say that the following data represent a random sample of the assets in millions of dollars for 30 credit unions in Colorado. It's not all of the credit unions in Colorado. Assume the population standard deviation is 14.405. Find the 90% confidence interval for the mean. And here the mean is the average assets in any given credit union in Colorado. There's more than 30 credit unions in Colorado, so the mu here would be the average number of assets in millions of dollars for all credit unions in Colorado, of which we've sampled 30 here. So we don't know what mu is, but we can calculate what x bar is by averaging all of these things together here. So once we've averaged these things together, then we can find out what that is. Let's also find out what the standard error of the mean is, and let's see if we can calculate a 90% confidence interval on that mean. So this is a good chance for you to exercise some of the stuff that we've been doing in the previous few slides. This is a time to see if you can calculate some of those same things that we were doing and come up with a 90% confidence interval for the mean. Take some time for that. Okay, welcome back. Well, it's not every day that you are estimating the average number of amount of money that's in all credit unions in the state of Colorado, but here we are. So this is a sample of each one of them. This is actually not real data here, but we do this in the same way if this were real data here. So from taking a look at all these sample values, and there are 30 of them, we have an average here of $11.091 million in each one of those credit unions. We know that the standard deviation there is 14.4, and so we're able to calculate what the standard error of the mean is as being 2.63. We're wanting to find a 90% confidence interval, so alpha here is equal to 0.1, and so the z-value that we're going to be using here is 1.65. Remember that from our warm-up there. And then if we take a look at this here, we're defining our confidence interval here as the sample mean plus or minus the z-value times the standard error of the mean. The z-value is here, the standard error of the mean is here. We multiply those two things together, we get the margin of error. And so in reality, so for our interval to be created here, we want to take the point estimate and add and subtract this. So we know here that from these data here that the average amount of money in each credit union in the state of Colorado is somewhere between $6.7 million and $15.4 million. Okay, now sometimes, and this is going to come up in the homework just a little bit here, sometimes they're going to ask you for some unusual confidence intervals, in that the percentage is a little strange here, like 98% or 96%. What do we do in those circumstances? Well, it's just the same thing that you did in the warm-up here. Everything is the same, except we just have to recalculate that z-value, that we have to figure out again what that z-value needs to be in order to hug that percent of the data, be it 98%, 96%, whatever it is. And so, for example, if we're asking for a 96% confidence interval, then alpha equals 0.04, and so we just plug it into this same formula here again. Alpha equals 0.04, we've plugged it in here. Order of operations says I have to do this division first before subtraction. The division here, 0.04 divided by 2, that's 0.02. Now I can subtract this from 1, I get 0.98, and if I pull that up on my normal distribution table here, 0.98, where is that? Well, probably the closest one right here is 0.9798, and that is at a z-value of 2.05, 2.05. And so you can see here, that's our new z-value. Everything else is the same. Now, there's something kind of cool about this. That is that since we have this formula that relates the size of the confidence interval and to the sample size, you saw how as the sample size gets bigger, the confidence interval gets smaller and smaller and smaller. And so oftentimes we're dealing with a desire for a certain degree of precision as we calculate our estimate. And so wouldn't it be nice if we could find out how many samples we need in order to get that normal distribution to squish down to the level of precision that we're after? Well, we can just take a look at our formula here, and we can talk about here, this is the margin of error that we're looking at. And so let's say we want this margin of error to be something specific. So all I've done here is I've taken this and I've set it equal to E. Oh, I also took standard error of the mean and I expressed it as the standard deviation divided by square root of n, just like we've been doing for the past couple of lessons here. So all I've done here is I've taken the margin of error and I've set it equal to some fixed value. I say I want to know the value of this average plus or minus this amount. I don't want to. I want it to be at least this precise here. So then, see, I know what this is. I know what this is. I want it to be, let's say, a 95% confidence interval or a 99% confidence interval. And I know what the standard deviation is. I can solve this for n to find out how many samples that I need in order to get to this. All right, so I'm going to solve for n here. Here what I'm going to do first is I'm going to divide both sides of the equation by this mess here. And the z is now here in the denominator underneath e, and that just leaves behind this and this here. Now, one of the things that I can do on both sides of the equation is flip both sides. I can take the reciprocal of both sides. That's okay. And that's exactly what I do here. Now, e is on the bottom. This z thing is on the top. The standard deviation is down here. The square root of n is here. Now, why did I do that? Because I'm trying to get n by itself here. And if I multiply both sides here by sigma, that's going to get rid of this sigma over here. It's going to cancel here, and it's going to make an appearance over here. I'm going to do that. I'm also going to switch everything so that I'm showing it, I'm going to turn it around here so that n is on the other side, and all of this stuff is now on the right side. Now multiplied by that standard deviation that I multiplied both sides of the equation by. So once again, I took the standard deviation here and I just multiplied both sides of the equation here by the standard deviation. And that causes these two things to cancel here. All I'm left with here now is the square root of n, and this is what I now have on this side. Now, what do I have to do in order to make it so that this is an n and not the square root of n? What do I have to do to both sides? Well, you guessed it. I have to undo that square root by squaring both sides here. So now it's n equal to this same stuff here, but now all squared. That's our answer. That's how we can find out the number of samples that we need in order to get a certain level of precision that we want. This is actually something that I had to do to some extent in my job, where there's some people who wanted to know something to a certain degree of accuracy, and I said, well, we can, with the amount of money that you've already budgeted, we can get it down to this level of accuracy. If you pay this amount for this many more samples, we can get it down to this. If you pay this amount more for this many samples, we can get it to this level of precision. And we gave them options on what they wanted to do here. But we did that based upon this kind of equation here, where we could calculate the number of samples needed in order to get the margin of error down to lower and lower values. Okay, so let's see how we can use this. A sociologist wishes to estimate the average number of automobile thefts in a large city per day, and she wants the margin of error to be down to 2 automobiles, and she wishes to be 99% confident in her estimate. From a previous study, the standard deviation was found to be 4.2. Okay, so how many days? What does her sample size need to be? How many days should she select to survey? Well, for this, here's our handy-dandy formula here. And let's see, we know that the standard deviation here is 4.2, so we're going to plug in 4.2 in for that. We want the margin of error here to be 2 automobiles. And we're going to get this from the fact that it's a 99% confidence interval here. And so alpha equals 0.01. We're going to plug that in for alpha, and we're going to find out that what we're looking for is z sub 0.995, and that'll be a specific z value from the warm-up. So again, e equals 2, standard deviation is 4.2. Our z value is this one from the warm-up, which is 2.58. Just plug everything in, and we get 29.35. 29.35 samples. Well, you can't take 0.35 samples. You either take a sample or you don't take it. So what we have to do is round this up. So she'll need to sample 30 days in order to get the precision that she wants. So her sample size needs to be at least 30. Okay, so to summarize all of this stuff here, this is a lot of really cool stuff here. Do you know how this new notation for z, first of all, the z sub something, that little subscript on z here means the amount of area to the left of that z value here. Second thing, how to calculate a confidence interval given a point estimate, the population standard deviation, the sample size, and the desired level of confidence. That is a mouthful. How to calculate this confidence interval given a point estimate, that's that. The population standard deviation, that's that. The sample size, that's that. And the desired level of confidence, that's, what kind of percent confidence we want, and it manifests itself as this parameter. So hopefully all of those symbols there are familiar, and so you can see that we've done this many, many times here. And lastly, how to calculate the necessary sample size given the population standard deviation, the desired level of confidence, and the desired margin of error. So once again, margin of error here, that's E. The population standard deviation, that's sigma. The necessary sample size, that's N. And the desired level of confidence, that's that percent on the confidence interval, which tells us what our alpha value needs to be, which tells us what our z value needs to be, ultimately. Okay, well that's really everything that we've been covering here. It's a lot of stuff, and there's a lot of good problems to practice this on in the upcoming assignments, so stay tuned. We'll be having a lot of in-class discussion on this, but enjoy this stuff. This is really, really cool. And what's cool is that in this next election, you'll be able to watch some of these estimates for some of these candidates. Biden's at this number of percent, Trump is at this percent, but at the bottom, you'll be able to see margin of error plus or minus this, and you'll know where that comes from. Good for you. This is good stuff. I'll see you in class.